this is our third and final technical session for today, and it is on laser plasma interaction, chaired by Professor Anand Murthy from RRCAT Indore. This exciting session will feature cutting-edge experiment work and simulation insight. So I call Professor Anand Murthy, sir. Please come on the stage. Now over to you, sir.
Thank you so much. So good evening to all of you and welcome to this last technical session of today. And as informed, it is on laser plasma. And there is one invited tutorial talk followed by 4 oral talks in this session. So for tutorial talk is from Dr. Vipul Arora from RRCAT. And for this, there is 40 minutes. So before that, I would very quickly introduce Dr. Arora to you. So as you all are aware, most of you, I think, and that RRCAT is a Department of Atomic Energy Center here in Indore, just nearby to this campus. And this center has basically program on lasers and accelerators. So lasers has basically the main mandate was on laser fusion. And for that, high energy lasers were ND glass based were set up here. And Dr. Arora is one of the researchers who joined this group, that is laser plasma activity, since almost beginning of the activity here at RRCAT, which was primarily shifted from Bhabha Atomic Research Center, Mumbai, where the laser program was initially started there. And then when this RRCAT was established for laser technology as well as accelerator technology. So he is one of the first experimentalist. He is very experienced experimentalist in the laser plasma interaction, particularly for X-ray spectroscopic techniques for characterizing plasma. And in fact, researcher from ITER project, IPR, particularly this Sanjeev Vasne, also visited us and worked with him for developing diagnostic, spectroscopic diagnostics for ITER project. So we started with nanosecond plasma, picosecond laser plasma as the laser technology evolved. And Dr. Arora is one of them who worked on all these aspects, starting from nanoseconds to picosecond. And now, as you must be aware, that we have now femtosecond lasers. So the pulse duration has, by techniques, it has come down to femtosecond, and the powers has gone up. So now we have high power ultra short lasers, which are basically based on chirped pulse amplification technique, a technique developed in 1985, and which revolutionized this laser technology in the ultra short, and which was given Nobel Prize in 2018 for this technique, CPA technique. So throughout the research laboratories, institutes, you will find these CPA-based laser systems, which are used in variety of ways, material science, chemistry, biology, and of course, we at RRCAT are using it for high power, that is petawatt. We were earlier having 150, and now we have a petawatt. The first highest power laser in the country is running at RRCAT. And Dr. Arora is involved with all these experimental activities. So now he is working on this high power ultra short laser interaction with metal targets for fast electron acceleration and X-ray generation, etc. So he will tell us about in his talk. And title of his talk is Laser Plasma Interaction at Extreme Intensities, Particle Acceleration and Intense X-ray Generation. So with this short introduction, I welcome Dr. Arora, please to give his talk.
Good evening, everyone. So thank you, Professor Murthy, for nice introduction. And indeed, I'm an old guy now. I'm working from nanosecond lasers to now the femtosecond facilities. So today I will speak on the recent current interest which I am working on, this laser plasma interaction at the extreme intensities. And the motivation is to develop particle accelerators and the intense X-ray sources. So this slide gives the broad overview and the motivation for the work. So this is typically we use the titanium sapphire lasers with a photon energy of 1.5 eV. And the pulse duration is typically tens of femtoseconds, the power comes to in excess of 100 terawatt. And when we focus it into the size of few micron on a foil of typically few microns to tens of micron, the peak intensity is when achieved greater than 10 to the 18 watt per centimeter square. So we have a copious amount of ions and fast electrons emitting from this source. So the interaction mechanism is very complex, and we need investigation to understand the laser energy coupling. And we call these fast electrons, which are in the excess of hundreds of keV to several MeV, and these are different from the thermal electrons, and this can be utilized. This can be utilized for various kind of applications. And other thing is the transport of this fast electron beam through this thin foil is also a very interesting aspect. And in morning talk, Professor Bandyopadhyay has told about the fusion schemes using lasers, where there are many difficulties regarding the wall plug efficiencies, and through another scheme called the fast ignition, we can reduce the power required for the laser system and improve our wall plug efficiencies. And the sheath field gives the high energy proton and ion beams. And of course, when this fast electrons travels to this target, they generate ultra short duration X-ray source, and which can be utilized for the time resolved studies, which is also a very interesting topic. And if we replace this target with a gas target, we can generate the conditions for acceleration of electrons from tens of MeV to several GeV. And also, this kind of acceleration mechanism gives the bright beta-tone X-ray source, which are suitable for a very interesting aspect called the phase contrast imaging. So, as Professor Murthy is told, that there is a rapid advance in laser technology which helps to improve this peak power of the laser systems. And initially, the growth rate is very fast, going from less than a kilowatt to the gigawatt with the development of technologies. But there is a lull between this 1970s, mid-70s to 1990s, the power doesn't increase much. And with the development of this Chubb pulse amplification technique, leads to the foundation for the development of terawatt to petawatt class laser system, which can be focused to achieve the intensity in excess of 10 to the 22 watt per centimeter square. So this is very important development in the field of laser matter interaction, because earlier there is a problem in amplification of the short pulses. The intensity becomes so high, it changes the refractive index of the medium, which leads to the focusing of the beam in the gain medium and lead to the optical damage. And the Donner-Strickland and the Gerard-Moreau, this is the work which Professor Murthy was referring in the 1985. They proposed that if we can stretch the pulse by introducing a dispersion time delay between the different frequency and get it amplified, and inverse time delay, and to compress the pulse, and so that we can achieve the power up to the petawatt and several petawatt laser level. And this work was recognized and was awarded the Nobel Prize in 2018. So we do have ultra short high intensity lasers at Laser Plasma Division at RRCat. This is our flagship project, TiE-Sapphire laser, which is giving 1 petawatt power, 25 joule of energy, and 25 femtosecond pulse. And this is the 150 terawatt, again the TiE-Sapphire, again medium, and it can provide 3.75 joule laser energy. So this is a tutorial talk, so I will give some brief introduction on what we are doing and why we want to study the interaction at the high intensity. So why it is so much exciting? So to understand this, we have to look into how the light interacts with the matter. It is essentially the electric field associated with the light, and the electric field is linked with the intensity by this relation. So extreme large electric field can be generated by the high intensity pulses when we focus it to a small size. So this electric field is, normally the generated electric field is compared with the Coulomb field, and with the test case is the hydrogen atom, where the Coulombic field is typically close to the 10 to the 9 volt per centimeter square. If the intensity is calculated, then the atomic intensity comes to 10 to the 16 watt per centimeter square. So the current highest intensity which is available is in excess of 10 to the 21 watt per centimeter square, and the electric field is 10 to the 12 volt per centimeter. So when this atom is placed in such an intense laser irradiation, it just rip apart, and we have the it just ionizes. And the interaction becomes so much exciting, and besides this, the high energy electrons can also interact with the system. So before looking at the matter interaction at the extreme intensity, let us see how the individual electron would behave when we place in such kind of electric field. So if the cycle average kinetic energy can be calculated, which we call the ponderomotive energy, by putting electron in the electromagnetic field, which comes to this relation. And if we use a 800 nanometer titanium sapphire laser and have a moderate intensity of 10 to the 16 watt per centimeter square, the ponderomotive energy becomes 600 eV. The electron energy goes to 600 eV, which is nearly 400 times of the laser photon energy which we have put, that is 1.5 eV. So we can call this as the acceleration of the ionized electron in the laser field. Energy is enhanced by the 400 times. And if we have a laser having a intensity in excess of 2 into 10 to the 18 watt per centimeter square, the ponderomotive energy can become more than the relativistic and rest mass energy, that is greater than 500 eV. And we can say that the interaction now become more than when we shine the laser at an intensity greater than 2 to the 18 watt per centimeter square. We say the relativistic laser matter interaction phenomena is occurring. But it has to be noted that no net energy is gained for the oscillating electron during the laser pulse. The electron which start from rest and oscillating under this electric field comes to the rest after the field is over. So how we can couple this energy to the plasma? So this is the point. So I will come to this first. The other thing is how this ionization take place in such a condition. We are aware that that multi-photon ionization mechanisms happens when intensities are excess of 10 to the 12, 10 to the 11 watt per centimeter square. But now our intensities are much higher than that atomic field intensity of 10 to the 16 watt per centimeter square. So when atom is placed under such kind of intensity, the Coulombic potential distorts. If you can see that there is a distortion of the Coulombic potential, and the energy of this gap, potential gap, does not remain infinite. And if the conditions are sufficient, that the laser frequency and the intensity, then the electron can tunnel out from this atom. And this is called the tunneling ionization scheme. And again, this when the intensities become excess of 10 to the 15 watt per centimeter square, the barrier gets suppressed, and the electron can just simply tunnel out, come out over the barrier, and which is called the over the barrier. So essentially, there is optical field ionization is the reason for the initial ionization of the atom placed under such a field. And for the tunneling, this is the laser intensity, which is essentially control this width of the barrier, and that is the inclination as well as the frequency of the laser field. This is the time available for the tunneling. So with this basic introduction, how this process is happening, let us see how this ultra short pulse laser matter interaction happen. This ultra short pulse, it is a light packet, a special packet of length approximately few micrometers, which is less than the breadth of the human hair. So the plasma, the energy is deposited into the plasma, and during this laser pulse, plasma does not expand, does not have a time to expand. So essentially, the interaction is taking place at the very high density, and the transition from vacuum to solid density take place over a very small fraction of wavelength, which we define as the scale length, the distance over which the density falls down by 1 over E over the critical density or the solid density case, as per the definition which is being utilized. So, and as I say, the oscillating energy of electrons becomes excess of 10 to the keV to MeV range as the electric field is very high. So the question comes, how this energy is being coupled? So plasma is not expanding much, and how this energy is coupled to this plasma? So it is important to see the laser energy absorption mechanism in such kind of plasma. So there are different ways through which the energy is coupled and based on the intensities. And first foremost is the collisional absorption mechanism, and where the electron which oscillate in the field of laser and get thermalized with the ions and deposits energy. But this efficiency of collision absorption decreases as the intensity increases. The collision electron-ion collision frequency decreases, and the absorption is not very efficient through this mechanism. So other mechanism which we call the collisionless mechanisms are being proposed, and one of them is the resonance absorption, whereas this is we have to shine the p-polarized laser light onto this is the plasma, which we have shown this is the density as a function of distance. When this p-polarized light is shined obliquely onto this plasma, the field is tunneled through the from the turning point to the critical density and excites the electron plasma wave. And this electron plasma wave is damped into the plasma either through the collision or the Landau damping or the wave breaking, depending on the conditions. And the electrons gets the energy. And for resonance absorption to occur, the scale length it has to be greater than a few micron, some micron to few micron, and intensity should be greater than 10 to the 15 watt per centimeter square. But what happens if the scale length is significantly low? In that case, the another mechanism was proposed called the Brunel heating or the vacuum heating, where the electrons are pulled from the surface of the plasma by the electric field, accelerated, and when the field reverses and damped into the target, and where they lose its energy. And this mechanism is applicable up to 10 to the 17 watt per centimeter square. As I said, the other condition is to match the, it is applicable for the very sharp density scale length plasma. And we also need a p-polarized light for this. What happens if you are having intensity in excess of 10 to the 18 watt per centimeter square? What I say is the relativistic intensity. At such intensity, the magnetic field of the light, laser, is also become important. So the electron which are oscillating in the laser field are also pushed into the plasma by the V cross B force. And this is a well-known mechanism which is discussed in early talk also, and we call the J cross B heating is happening. So the end result is the acceleration of the ionized electron, and to impart them a high energy which we call the fast electrons. So now there are how we can understand this mechanism through which the energy is being absorbed by the plasma. So there are various methods one can do, and one of the simplest method is to measure these fast electrons. So the simplest is you just measure the angular distribution of the fast electron beam. If the resonance absorption happens, the emission comes along the target normal direction. If the vacuum heating is that again the emission comes along the target normal direction, then you have to distinguish either by having the estimate of your density scale length. And J cross B heating, the emission of the fast electron would occur along the laser direction. And the flux and temperature of fast electron is also polarization dependent, as I say, is that resonance absorption and the vacuum heating is applicable for p-polarized light, and where J cross B acceleration mechanism happens for both P and S polarized light. So a researcher can do a simple measurement of the fast electron angular distribution, its spectrum, to find out what is the basic mechanism is happening inside the plasma. So, and this mechanism is not as unique that it is happening that only one mechanism is applicable at once, and it also depends on your conditions, interaction mechanism, what are your laser pulse duration, and is another parameter is called the contrast. Is there any pre-pulse activity before the main laser pulse which may destroy, which says the plasma is having a very long scale length, is not sharp density gradient, and these are things are also material dependent. So essentially, by making a simple measurement of the fast electron spectrum and studying through through variation of the laser and target parameter, one can identify what is going inside the plasma. So I will show you some of the experimental investigation which is done in our division, and what are the future direction one a researcher can take with this kind of with this kind of measurement. So as I say that to measure the angular distribution, one can utilize a very simple setup. These are the phosphor screen. These are the phosphor screens which can be used, and these are as we have used a 3 DRG screen, and we can measure, we can use the CCD camera to capture these images, and from this we can find out what is the angular distribution, and if we have the beam along the laser direction, it is the J cross B heating. And these are the few observations in my lab which we have done, that we have first time demonstrated the ponderomotive accelerated fast electron, which is the clear-cut signature of the J cross B heating. And the other thing which we have observed, that the temperature is much less than the ponderomotive energy. In my initial slides, I try to impress you that the ponderomotive energy, which is the thing, the cycle average kinetic energy, become very high. And even in high intensity ultra short laser matter interaction, if kinetic energy is not that high, then we have to look for the reason, what happens. And other thing is that we observe that even in J cross B heating, we saw the strong polarization dependent role. So these are the small observation which gives some insight into the plasma. I will share you with some results. So these are the images on the DRG screen. You can see in the 3 images, and the bottom slide is the. So this is the angular distribution. We can see that the beam is along the laser direction, and there are 2 beam also along the side beams, transverse beam, due to the escaping of the oscillating electron in the laser electric field. And we have measured this angular distribution for wide range of the parameter, and the pattern remains similar, and with the change of the targets and as well as the intensities, because we are working in the much higher above the relativistic intensities. And the transverse beam are the flux is low. It is maybe because they are escaping oscillating electron which are coming in the initial part of the laser pulse, and that is why the flux is low. And this is the first observation of this kind of the side beams, and which may occur because the laser pulse has some Gaussian profile in the initial foot, and where the V cross B is comparatively weaker. So the electrons are escaped by this along the laser polarization direction. The other thing which I have mentioned, that the ponderomotive energy was low, much lower. So what we have seen, these are some scaling laws which are given, that ponderomotive energy, relativistic ponderomotive energy can be calculated through this formula. And for instance, at 10 to the 19 watt per centimeter square, one can expect a 700 keV type of ponderomotive energy, but we have measured the 120 keV. So what is the reason? So most of the electrons are not able to see the full ponderomotive potential. They are even escaping, seeing the quarter of the potential. And this is true in our case because we are having the high contrast laser matter interaction. The scale length of the pre-plasma is much smaller. And all this measurement were done at the rear side of the target, and where the electron has to lose the energy in combating the sheath field. So this is one of the 2 reasons which we have found out why this energy is low. But the point remains same, that if energy is low, how could we have increased this ponderomotive energy? So the idea that we got the clue that it is the sharp density scale length which is acquiring the full potential, ponderomotive potential. So we have used a dedicated pre-pulse line. We have deliberately increased the scale length of a plasma by using a second pulse. And we have estimated the scale length using a 1D hydro codes. And this is the spectrum of the fast electron for the different delays between the pre-pulse and the main pulse. And we can see that the temperature, by temperature here we mean that the electrons have a continuous energy distribution. if you plot, it is a slope of the spectrum with the energy, and this is defined as a temperature. If you put a Boltzmann distribution also, which is the slope of the spectrum, one can find out the temperature. So we note that in the presence of pre-plasma of longer extent, this electron temperature is become higher and even become higher than the ponderomotive energy. And one explanation is that it is well known that the pre-plasma helps in increasing the absorption of the laser light, and which is leading to this kind of behavior, and which we later on probe further, that it is another mechanism which is, I'm not showing in this presentation, other mechanisms are also started to operate, which we call the stochastic heating. And in presence of longer pre-plasma, this wave field acceleration can also occur, but for that the energy could become very high, so that was ruled out. So my point is here that by measuring the simple things, and one can find out what is happening with the laser matter interaction at such extreme intensities, and the ponderomotive energy, which is everybody wants the electrons of very high energy, and by using a simple way, this electron energy can be increased. And another aspect is that what I told you, that polarization dependence of fast electron, which is another thing which I have proposed, that role of pre-acceleration. As I said, that the J cross B acceleration mechanism predicts that it should remain same. It should not differentiate between the p polarized and s polarized pulses. But what we have observed, that if you see the electron flux for p polarized and s polarized light, significantly lower for the s polarized light. If you look for the electron charge, it is again decreased. The spectrum, we can see the temperature, and the endpoint energy is also it changes with the polarization. And even in case of transverse beam is expected, because the polarization direction for the s polarized beam in the vertical direction, so electron flux is not expected. So what is the reason for reduction in this charge for when even the interaction is occurring at such a high intensities, and where the clear-cut signature of J cross B acceleration was shown? So to explain this, we conjecture that in the initial foot of the laser pulse, the electrons are generated through the polarization dependent mechanism, and which are further accelerated by the J cross B acceleration mechanism, which we call the role of pre-acceleration. There is some sort of pre-acceleration is happening inside the plasma. Now the question comes, then why we are seeing the beam along the laser direction? Now the main momentum is coming. Initial momentum, which is very small, is along the target normal, and the main momentum is coming along the laser direction, and so net effect is to see the beam along the laser axis. So this is the one of the work in our lab we have shown can be happening. Other thing is, in morning we have discussed the transport of the fast electron. In the morning it comes to that the laser fusion, generated fusion has a lower wall plug efficiency. It is true that we need a higher power laser systems to achieve the really gain, and can we reduce the energy of our driver, as well as there is a very much requirement of the symmetry. If this requirement can be relaxed, so it is proposed that the ignition of the fusion capsule pellet should be done by this accelerated electrons. And please note that initially, when the nanosecond laser plasmas were used to compress and do the ignition, these fast electrons were considered to be disadvantaged because they can preheat the target. So now this comes to our advantage. This fast electron can ignite the fuel. So it is necessary to see how this fast electron propagates through the plasma and deposit their energy. And please note that this current is mega amperes, and when mega ampere current is flowing through this solid target, so it generates the azimuthal magnetic field which try to pinch the plasma, and when this electrons escape from the rear surface, it generates the sheath field, and which can, I will show you in my further slides, it accelerates the ions to very high energies. So, and this collisional effect, when these fast electrons are propagating, it generates the X-rays, and if you have, which can be continuum Bremsstrahlung as well as the monochromatic inertial line radiation, which can be used for diagnosing the plasma as well as for practical applications. And other thing is that electron refluxing due to sheath field, because sheath field would form at the both the surface and it will not allow the electron to escape from the target. And this, if you say that there is, when such a high current is propagating through the plasma, it is not allowed to pass unless there is a return current originating from the target. So this is a very exciting field for researchers to start working on it, right from the generation of high energy ions and for contributing in the fusion research. So, and so we have done some fast electron transport studies. We have utilized the X-ray which are being generated in this interaction, and we have set up a spherically bent quartz crystal to get the two-dimensional images of the X-ray source. And as we know, the imaging of X-rays is this is not possible. So we this quartz crystal, which is based on the Bragg reflection geometry and also act as a mirror, it can give the images of the X-ray source, and is the front side image, which is now this fast electron which are generated at the front surface. The source size is essentially of the order of the laser focal size, which is a few microns. But what we observed that the X-ray source size is much larger. So that gives us that there is a lateral scattering is also happening over the surface, and which is enlarging the size. So through the simple measurement of the X-rays, such kind of measurement can be done. So how this electron divergence is evolving? It is difficult to measure the electron divergence. From direct measurement, one cannot have this electron divergence measurement. So what is happening when the electrons are propagating through the thin foils? So we have seen this source size at the two different thickness foil, that is 7 micron and 25 micron, and the source size increases, and from this simple relation we can find out what is the divergence angle. Please note that divergence angle is much less, 17 degree only we have obtained. Why? That shows that this is because of the collimation effect by the azimuthal magnetic field, which is generated due to the propagation of the high current beam into this thin foils. So another thing one can do, one can use a simple layer targets. I'm telling these are the simple experiment which can give the insight into what is happening at the extreme intensity cases. So for instance, we have used two foils. We have used a fluorescent foil of the copper, which is of the 0.7 micron, and transport foil of the nickel, which is 5 micron, and another is 12 micron. What we have observed that for thicker foil, the flux is almost 10 times smaller. And the reason is that the electrons, this X-rays which are coming, it is because of the electrons which are confined into this target, what we call the refluxing. Because of the sheath field, the electrons are not able to escape, and they are losing their energy in generating the X-rays. So with the thicker foil, the weaker sheath field is formed, and that is why we are getting the lower flux. It has also implication in other application which I will show. Okay, another thing is that we have used the copper foil to generate this monochromatic alpha X-ray source. You can change your target material from molybdenum to 17.5 keV, silver 22 keV, and you can have a ultra-fast probe which one can utilize for the radiographic imaging for high Z and dense material, and these probes can be used for time-resolved X-ray diffraction studies for dense objects. So this kind of experiment is also possible with this laser matter interaction at the extreme intensities. Okay, this is the practical application. Which when this is the what I have shown. This is the laser pulse having the intensity greater than 10 to the 18 watt per centimeter square. It is impinging on this target foil, which we kept sufficiently thin, and when electron escapes through this foil, it generates the sheath field, negatively charged sheath field, and this sheath field is so strong that it ionizes the atoms and rapidly accelerates the ions normal to the surface. This sheath field, as you can see, it depends on the temperature of the hot electron and the fast electron density. So as we, in the previous slide, what I have shown, that if you have a thicker foil, the source is diverging, so the fast electron, number of fast electron per unit area decreases and the sheath field decreases, which is not able to confine the electron into the foil. So this is simple number which we have calculated. If you take that fast electron beam of 1 MeV and the extent of 1 micron, the sheath field of 10 to 12 volt per meter can be generated. So this is the ultra compact source, micron size, and this field of 1 to 10 teravolt per meter can give a proton beam, ion beam of 10 MeV over a distance of 1 micron. So if to impress the audience, I will briefly give you why this our ion beam of few tens of MeV is so important. If you look at its ion beam property, first of all, I say that our source is ultra compact, and even over a distance of few micron, we can accelerate to few tens of MeV. The particle flux per bunch is very high. Charge is of the order of nanocoulomb, and this source is generated by the ultra short laser pulses, and the sheath field exists for the duration of few picosecond, order of picosecond. So the duration is extremely short. If you compare with the conventional RF beams, which is of the nanosecond duration, this is a ultra short duration source, and the emittance is also less than 0.1 millimeter millirad, and size is small. One can use this for some imaging application and proton radiography, and divergence is also not very low, but it is considered to be less, 10 to 20 degree in cone angle. And not only the proton, but we can also accelerate different ion charge species by this, and by simply changing the target. You can have the carbon, you can have the copper ions and gold ions. And another thing is because it exhibits a broad energy distribution. So this is a negative point which we can tailor by using some beam optics. We can focus this beam to a quasi-monogenetic and using a magnetic and RF device. So this gives a new field that can we do the laser-driven proton oncology, which can be a new cancer therapy. And another thing is, in the morning we have discussed in the laser fusion that proton boron, neutronic fusion schemes. So these proton beams can be utilized for this proton boron fusion schemes also. So these are the few areas which is very exciting to work on, and for a researcher in this field. This is a few traces which we have recorded. This is the Thomson parabola traces. You can see the proton beam and carbon beams. And these are the ion population as a function of ion energies. We have also used the radiochromic film stacks. You can see that high energy beams are much smaller in size, which is expected. The divergence is low. And okay, another scheme is if we replace the target, solid target by the gas target, we can accelerate the electron to a much higher energy, up to few GeV energy. And my colleague Shikha will speak after one or two speakers. She will tell more about the laser wake field driven electron accelerator, where the pontomotive force of the laser generate the electron plasma wave at the wake of the laser pulse, and it can have a longitudinal field which can accelerate this electron to a very high energy on a very small length, and which is a promising scheme for generating a very high energy electron beam for application for injectors for the future accelerators. And these are the typical experimental setups which in our lab which is used, and time is less, and Shikha will tell you more on this kind of setup what we are using. And another thing is, this is my last slide. Not only the longitudinal acceleration of the oscillation of the electrons along the laser field, electron can also oscillate transverse to the propagation direction, which we call the betatron acceleration. This happens when the electrons are injected not along the laser or the plasma wave axis. So this is we call the betatron X-rays, and this X-rays wavelength depends on the electron beam energy and the charge of the beam. And the most important point is this is ultra short duration X-ray source, and the size is few micron. So coherence length of this kind of source is very high, and and again the compact size and the low cost X-ray source for performing another thing what we call the beta, this which we call the phase contrast imaging. This is the work which we have done in our lab, and this is the image you can see. This is not possible in the absorption imaging with mosquito, which is very thin absorber. This is what you call the antennas, and sitting on the leaf, which is recorded, and we have also done some physical object, and this kind of phase contrast imaging is possible because the coherence length owing to the small X-ray size is possible, and this kind of experiment is done in the Indus X-ray sources, and at labs such kind of sources are available for performing this kind of studies. And moreover, it is the ultra short source. If somebody want to do the time resolved measurement, these things offer a best alternative, I would say. So in conclusion, I will say that the availability of hundreds of terawatt and petawatt class laser system makes us possible to investigate the interaction mechanism for intensity in the range of 10 to 18 to 21 watt per centimeter square, and we generate the fast electrons, and which can be utilized for understanding the basic laser matter interaction mechanisms, and the transport, which is very important aspect, can be studied using the X-rays measurements, ion acceleration, which is due to the sheath field formed by the escaping fast electrons through the thin foils, and this ion beams can be utilized for many more applications, and interaction with the gaseous target give you a GeV class of up to GeV class of beam and betatron X-ray sources, which is suitable for phase contrast imaging. So essentially, the interaction at extreme intensities open up a new avenues for particle acceleration and the X-ray generation. So I acknowledge Dr. Chakera, Head Laser Plasma Division, Professor Murthy, who is heading this activity of advanced laser acceleration, and these are my colleagues who are working with different aspects. Tirth, B.S. Rao, Tayyab, Shikha, she is also doing PhD in, and Ria working on the transport aspect, and Shivangi, a new joinee, who has also started working in this ion acceleration schemes. Thank you very much.
Beautiful presentation, sir. Thank you so much. I just have a couple of questions. Like you said, you are using a foil, which is basically micrometer in thickness, and you shine laser and you produce high energy beams. Now, that is a very thin foil, and when you shine such high intensity laser and ions are being thrown out continuously, and how long does this foil live? I mean, how long can you produce intensity ion beam? That is one question. And
go one by one. Go one by one. Yeah.
Okay.
Let him answer first. Yeah.
When we interact the high intensity laser beam onto foil, the foil gets ruptured. So this is a single shot measurement, and we have to move the foil for the next exposure. And the ion beam which are generated during the laser pulse only.
Okay, so you mean to say that we have to keep changing the position?
So this is we have to keep changing the position of the foil.
Fine. And why not we don't talk about electron beams being generated in this kind of idea? Why is it ion beams?
So electron beams are being generated in the laser solid interaction, which energy is up to hundreds of keV to few MeVs.
Okay.
And their applications are different. And other scheme is if you shine the gas target, low density plasma interaction, there you can generate the the high energy GeV class, up to GeV class electron beam through the mechanism we call the laser wake field electron acceleration, and even the direct laser acceleration. Because the toxicity of the time, I could not speak on it, but don't mind that now my colleague Shikha will speak on this after just wait for 20 more minutes.
Okay. So gas targets are exclusively meant for electron beam production.
Yeah. If you want to have the beam of very high energy, if you want to replicate the accelerator, as I say that if you have a GeV class of beam of a few hundreds of MeV beams, then that can be utilized even for the injectors in the convention accelerators. And this kind of beam can also use for generating the betatron X-rays. You can use the inverse Compton scattering to generate X-rays. So there are a variety of applications for those kind of beams. And
All right.
Yeah.
And I have
Maybe
a
you
small
can
doubt
give-
where you have several targets specified, gold and everything.
Yeah.
If I would ask you, in your experience, what kind of target you choose to get a very good pure ion beam, what would be your
okay.
answer? I
The-
mean,
so for-
what target you
see,
specifically look for?
We want to use a thin target for
Okay.
our case, and the thin target typically we have used from gold to aluminum and everything we try to use. And in our experimental purpose, mostly we use the aluminum target. Thinner targets are available with us, and we got a good quality. beam.
There could be some structuring of the targets or
Yeah.
shaping of it to have much more collimated and quasi-monogenetic beam. That is always a part of research.
Okay.
That's keep
Nano-
on going.
nanostructuring
So
can
you
be
are
done-
basically hinting towards getting the good quality beams, right?
Yes,
So
yes,
plain
yes.
target may not give you that good quality, but you may do something like having a shaped target or
Yeah,
something
nanostructuring can be done,
like
and
that.
nano
So
patterning.
it is
can be
still
done.
open area of
Sort
research.
of engineering the
Or
target.
some
a bit.
target engineering
Okay,
maybe
fine.
required.
And one final
Yeah,
question
maybe
is
I
such-
think let us give chance to others
All
also.
right.
You may discuss, Dr.
We can
Arora
discuss
is
later.
here. So, any other question, please, from others? Any other question? Okay, so I think let us thank Dr. Arora once again for this next talk. Now we move on to oral talks, and we have 4 oral talks in this theme. So the first one is from Rakib, right? SK Rakib from TIFR Mumbai, and he will talk about capturing the 3-dimensional nanoscale picosecond dynamics of plasma mirrors with intense ultrashort laser wavefront measurements. So Rakib, you have 20 minutes. I will remind you after 12 minutes, you should finish within 15 minutes. Yes. So we want at least on oral.
20 minutes, I think.
We will have discussion. Don't worry too much about. At least we expect some questions. So
Okay. Hello, I'm Rakib from TFR. And first of all, I want to thank Professor Arora for giving a very good overview of the thing. So it makes my job very easy. So today I'm going to discuss a very recent measurement that we have done at TFR. And I'll try to keep things very simple. And let's see how it goes. So yeah, so this is our 150 terawatt laser at TFR with a temporal FWHM of 27 femtoseconds and energy. It can deliver energies up to 3 joules on the target. And you can see the green lasers are actually used to pump the actual laser that we want to produce. That is 800 nanometer sapphire laser. And okay, so this is the scene of action. What happens is we have this laser, and what we do is we focus the laser beam to a few microns, like 5 microns to 10 micron. And with this tight focusing, we can reach intensities of the order of 10 power 19 watt per centimeter square, which is above relativistic intensities. And this can heat up the target material. Basically, it ionizes the target material, and it can produce all sorts of radiation from X-rays to gamma rays to higher order harmonics of the laser that we have sent. And also it generates MeB electrons, protons, and neutrons, as Professor Arora has discussed. So it can also generate very high magnetic field in very high magnetic field in the center region where the laser is focused. And I just want to give you a very essence of how it goes in the lab. So I have 2 videos. So if you see the bottom video, so we have a target and the laser is focusing, and then plasma is created, and the plasma, after the laser is gone, the plasma is exploding. Okay, so that's the thing. And here we are focusing the laser in air, and when we focus it in air, there is a phenomena called supercontinuum. So we send a 800 nanometer laser, which is like a red color, infrared, but we get all sorts of color from the focusing. So it's called the supercontinuum generation. So these are sort of things that we do in the lab, and what we want to understand is when we have this laser matter interaction, after the laser pulse is gone, the plasma is very hot and it tries to explode, right? So my work is basically how can we measure the plasma surface as it explodes. So in the femtosecond time scale, I want to measure the surface of the plasma, let's say, 3-dimensional. So is there a way to measure the rapid plasma surface evolution in real time? The answer is obviously yes, otherwise I won't be here. So let's see how we can do it. So we do it by measuring the wavefront in real time. So now, first question will come is why wavefront, right? So there are like other methods by which we can probe the plasma, we can see what's going on inside the plasma, are like Doppler spectrometry, frequency domain interferometry, cytography, and there are many more techniques that can give you information about what's going on inside the plasma. But all these measurements have some difficulties, they have very low spatial resolution, like Doppler and FDI measurements. So they are like, you can measure at a few points, but the plasma is expanding in 3 dimensions, so it's better if we get a very good spatial resolution of the thing. And some of the measurements are not very direct. So for example, in Doppler, we measure the velocity. So in Doppler, what we do is, let's say we send a probe pulse and then record its spectrum, and when its spectrum changes, with like plasma has a velocity, and with it the spectrum changes, and then from the spectrum change we can calculate the velocity. But so these are not like very direct measurement how we can like capture the 3-dimensional thing. Our wavefront measurement actually solves all these problems, and it can give us spatial resolution of like 10,000 points. So in one shot, we can like measure 10,000 points on the face of the plasma. Okay, so now what are wavefronts? We all know wavefronts. So wavefronts are a surface defined by points of same phase, right? Now this we all know from the schools, but what we don't know is how to measure a wavefront. So let's say there we have a planar wavefront coming, and then we have a lens, and the lens is basically focusing the light, and then you have a spherical wavefront created. So let's say we want to measure this spherical wavefront, how we can do, right? So, we'll make a very simple wavefront measurement device that everyone can do at home. So we can take a cardboard and we put some holes in it. So when we send a light, and then let's say we put the cardboard here and we put a screen after some distance. And then we send the laser, and then we send any light, not necessarily laser. So we send any light through this mask, whatever hole we have made, and on the screen we record it. So we know how, if it is a planar wavefront, on the screen the spots should exactly look like the mask that we have put, right? So in a planar wavefront, it will look something like that. And if the wavefront is distorted, it will, on the screen, the spots on the screen will be distorted than the mask. So by this technique, we can, like, in home, we can measure wavefront, but these are not very accurate, right? So researchers have been done how to measure the wavefront. And in 1960s, this Sack and Hartman, they invented a method, which is, so let's say we have an array of holes, micron-size holes, and then we put some lenses inside those holes, okay? And then we have an array, and then holes, and inside the holes, we have these lenses. And then we send the light, okay? So, and then what we do is we put the screen on the focal length of the lenses. So let's say that is the screen, and on the screen, let's say I know if my wavefront is planar, the focus of the laser will exactly be at the focal point, right? So it will be in the green dots, let's say. And then when your wavefront is like a curved wavefront, let's say you have a converging beam or you have a diverging beam, the lenses will focus somewhere else, right? The lenses will focus at the focal plane at somewhere else. So we can, if we replace the screen with a CCD camera, and then we know exactly where the planar wavefront should come, and then from the difference, we can actually back calculate whatever my wavefront was. So this has been developed in 1960s, and then very recently in 2000, there is a new measurement, new method of determining this wavefront is called quadri-wave lateral shearing interferometry. So let's try to understand what's happening here. So the idea is very simple. You have a grating, and then so if you send a light, what will happen? The grating will diffract, right, at different orders, and it has a phase plate. So what it does, the phase plate will come also in the we'll see some pictures. So what the phase plate will do is, so you have, if you have a grating and if you send a light, it will have different orders. Let's say you have a 0 order, then you have a first order. So this phase plate is designed in such a way that it will only keep the first order and it will eliminate the 0th order. For example, here, let's say I have a 1D grating like this, and then I send a Gaussian beam. And if we measure the intensity at, let's say, 20 mm distance from the screen, we can see like the brightest one is the 0th order, and then in the two sides, you have +1 order and a -1 order, right? Now, if we replace this 1D grating with a 2D grating, what will happen? Instead of these two blobs, you will have multiple blobs, right? So if you see at the 20 mm, you will see a central blob, and then in the y direction, you will have 2 blobs, in the x direction, you will have 2 blobs, and you will have other orders also in present, right? Now, if we put this phase mask with this grating array, so we have the grating and we put this phase mask, what it will do is it will eliminate everything other than the first orders. So if you see, now you see that only like the central 4 orders are there, that those are the first orders, okay? And the method is like you measure the interference of these 4 orders, and from the interference pattern, we can actually back calculate what the wavefront was. So I just want to show you, let's say we have only a grating like this, and there we have a grating plus phase plate. And what I'll do is, so you have this grating and phase plate, you have the light, and then I'll put the screen at different places, and I'll see the intensity, okay, how it looks. So this is for the grating only case, and that is for the grating plus phase plate. So distinctively, you can see like here you have a central spot, and other spots are like this, but there the intensity is distributed only in the first 4 orders. Okay, so the idea is we put a CCD at some distance, and then we record the interference pattern of these 4 orders. And from the interference pattern, there are like methods, how can we extract the phase map. So we can extract the phase map, and from the phase map, we can talk about the wavefront, okay? So we have like calibrated our device with this. So we have put a lens in the beam, and then at different places, we have measured the wavefront. We have, so this side you can see the converging wavefront is there, and then the diverging wavefront is there. So in a converging wavefront, the central part is lagging behind than the other part, and the diverging wavefront, it's like central part is going fast, and then the side part comes. So we have also like measured some other targets. Now this wavefront measurement technique has become very popular in biology. So they are like, nowadays they are measuring this cells and all with very nanometric precision. So these devices can measure like distances up to few nanometers. So so they are doing it. So we thought, why don't we do some plasma stuff with this? So coming back to the plasma. So the plasma conditions are evolving in femtosecond and picosecond time scales. So when the femtosecond laser is gone, the plasma basically explodes, and we want to see how this plasma is exploding as time elapses, right? And in femtosecond time scale. So how to do that? The answer is we have to do ultra-fast pump probe techniques. So, for general people, I'll just say what a pump probe technique is. So let's say we have this laser beam, very intense laser beam. What we do is we take a very small part of it and we make it a probe. So we delay it with delay stage, and then when the main pulse comes, we just delay the probe pulse, and then the probe pulse goes and interacts at the same point wherever we have focused the pump pulse. So let's say we have focused the pump pulse at that point. So what we do is we take the probe beam, we give it a variable delay, and then we send to the same plasma. So plasma is created, and then we are sending a probe beam just to pinch it and see whatever is happening. So we take the reflected probe pulse and put our detectors, like our detectors can be phase measurement device, reflectivity device, or anything else. So I'll just skip these things. So when this laser matter interaction happens, the electrons inside makes this figure of 8 motions. And then when our field is very strong, it will just deviate, like what we call a ponderomotive force. Due to this ponderomotive force, the electrons will also drift in the laser direction. So basically, we want to capture this kind of motions. So this is our setup. So we have the pump pulse coming in, and then we also take the probe pulse, and with the retrometer, we control the delay, and then focus it at the position where the pump is focused, and we take the reflected beam and send it to the detector. So the idea is very simple. Idea is, suppose we have a planar wavefront, and it reflects from a rippled surface. So the planar wavefront will actually capture the rippled surface structure, and if we measure the wavefront of the reflected surface, we can get information about where it is reflecting from. So here the idea is, let's say we have the plasma here, and it is expanding like this. So some part of the probe is coming and not interacting with the plasma, and some part of the probe is coming and interacting with the plasma, and there will be a time delay or space delay between these two parts. And then if we do some mathematics, we can actually relate this path difference between those two pulses with the position of the critical surface. So this is the result. So if you see at -6 picoseconds, -6 picosecond is when probe is coming fast. So probe is coming, and now pump has not arrived because we are coming before, okay, 6 picoseconds before. So it sees a planar target surface and reflects back. Now when we come at the same time when the pump is there, that is 0 picoseconds, and then when pump arrives first and then the probe arrives, we call it the positive delay. So all the positive delays are like probe is coming after and seeing the plasma and going back, and then we are studying it, okay? So if we see that at negative delays, we have a planar wavefront, like planar surface, and then at 0 picosecond, if we look at the center, if we look at the line cut, it will be maybe easy. So if you look at the orange curve, it is dipping, right? So that is due to a phenomena called ponderomotive push in the plasma. So the laser pulse has main laser pulse will put, because of the high intensity of the pulse, it will push all the electrons inside the matter, and then this dip is created. And after that, when the laser pulse is gone, main laser pulse which created the plasma begins to expand. So this is the expansion that we see in real time, right? Okay. So we have also compared this measurement with our previous measurements where we have measured the velocity. So here we know the position of the critical surface, and then now from the position we just take a time derivative and compute the velocities, and the velocities match quite well with the previous measurement. And we also do some PIC simulation to to validate our measurements. And this is the conclusion. So we have mapped the plasma surface in real time, and this has a very special, very high spatial resolution, like 10,000 points. And the measurements is very simple, and it is super efficient. So you can read my paper if you just scan the QR code here. And we are also doing other measurements with this wavefront sensor with the plasma. So this is our team at TFR. We call it Uphill family. Our group name is Uphill. And then thank you all for listening.
Okay. Thank you, Rakib. So presentation is open for discussion. Any question, please?
When you target the sample with your different pulse probe, so what actually information you want to measure in plasma? That is one. And second, how you measure the magnetic field, which is greater than 10 to the power cube Tesla when you shine the laser in the target?
Yes. So first question is, it depends. So whatever property we want to measure, let's say we want to measure the velocity by which the plasma is expanding. So we do a Doppler spectrometry. So we do Doppler spectrometry. And for this case, we have measured the wavefront of the reflected light. So we have measured the probe pulse reflected probe pulse wavefront, and at different times we have got different wavefronts. And then from the wavefronts, we infer how much it has moved, right? And to come to your second question is, so to measure the magnetic field, you can use the same pump probe setup, but what we call a polarimetry setup. So there you have to send so we send the a pulse, and then we, let's say at various combinations of, we put various combinations of polarizer in the reflected beam, and then we try to characterize the polarization. So because of the magnetic field, the polarization of the input light will change. And then we measure the polarization, and from there we infer the magnetic field.
Thank you.
Once the plasma forms, the type of sheath that has been formed, I'm quite concerned what type of sheath it has been formed there. Because you are giving the pulse.
Okay, so if I just go back, so okay. So when this plasma forms and then it tries to expand, right? And then let's say it has exponential profile like this, and then when your probe pulse comes, because inside the plasma you have the dispersion relation, which is written above, omega square equal to omega p square plus c square k square. So if you have an input light of omega, let's say, it cannot go beyond a certain distance inside the plasma, because otherwise it will either get reflected or it will get absorbed or evanescent in the plasma, okay? So it always captures, so from where the light reflects, we call it the critical layer of the plasma, okay? So whatever the light we are sending, let's say we are sending a 400 nanometer light, we are sending a 800 nanometer light. So this critical layer position will change with whatever omega we are sending. And then we are just seeing at that surface, where is that surface, critical layer in the plasma.
Okay, you are not like discussing on sheath and all.
No. Yeah. Yes.
Yeah, maybe last question here.
Nice talk. I have two questions. One is that what kind of phase filter you have used for your real experiments?
What kind of?
Phase filter you have used for your...
Beam splitter?
Phase filter.
Phase filter you said.
Phase filter?
Yeah.
So actually we don't use any phase filter. So what we do is, let's say we...
Sorry, I can rephrase. Means you said that you have to put some grids in between to identify the phases or the...
What was your actual wavefront measurement? This grating based, or it was?
Yes.
It was grating based. So you
Yes.
showed you put some phase mask before
Right.
So he's asking about that.
So what kind of phase mask you have put?
Use.
Okay, so it is a lambda by 2 phase mask. So if I go back in 1 second. Okay, here. So if you see this white thing and this dark thing, right? So in the white thing, the light just transmits, and in the white, gray thing, it goes through a lambda by 2 plate.
Okay.
So each like alternative alternative holes have either 0 phase or pi phase, like lambda by 2. Yeah.
So how many pixels you have used for your CCD?
This is 10,000 pixels.
10,000 pixels.
Yes, yes. So 10,000 is the count of, yes, 10,000 pixels basically. So it's 100 by 100 grid.
Okay, thank you.
Yeah.
Okay, so and what was the plasma spot size?
The laser spot that we send is like 7 micron, and then the probe is slightly bigger than this. So probe is something like 100 micron.
So within 7 micron, you are getting 10,000 points,
yes.
along
Not
the
7,
all
like,
the probe,
yes,
total
yes,
probe.
on the probe.
And
yes.
in the last figure that you are seeing, Z axis is
Z
basically
axis.
length,
Yes,
right?
yes,
Can you
yes,
go,
yes.
maybe that you should have that in nanometers, right?
Yes, that is in nanometer.
Last one, yeah, the final results.
This one you are saying?
Yeah.
Yeah.
So here,
So this
it's
is in nanometer. Yes.
This scale is from 220 to
440. Minus 220 to 440. Minus is plasma is going inside.
going
let's say.
inside.
And the plus is like it's coming out.
So any kind of calibration for this length?
Yes,
the
we
system?
have like.
That
So this I skipped because I didn't have time.
So you have done that, right?
Yes,
So you
yes,
have
we
calibrated
we
your
have.
this length and
Yes, yes.
okay. Let's thank Rakib for this nice talk. Yeah.
Hello everyone, myself Sakti Kushwaha. I'm from IPR and second year research scholar. The title of my talk is Study of Interaction of Ultra Short, Ultra Intense Laser Pulse with Inhomogeneous Plasma. And I today present a very specific topic, validation of electromagnetic field profile and absorption at different polarization in collaboration with Professor Sudeep Singh Gupta and Dr. Mrityunjay Kundu. The outline of my talk is first I tell introduction, then theory and governing equation, analytical, numerical and simulation parameters, and then electromagnetic field profile at different polarization, S polarization, P polarization, circular polarization, and the absorption mechanism at different polarization, S and P. And finally, I conclude my talk. So the motivation is the laser energy absorption in a plasma is crucial for inertial confinement fusion, electron heating, and laser plasma wave field accelerator. Absorption depends on plasma inhomogeneity, incidence angle, and different polarization. In this talk, I analyze the absorption of linearly polarized wave in cold, collisional, and non-collisional inhomogeneous plasma by examining the spatial electric field and the absorption across various angle, scale length, and the collisional frequencies. Here there are the two absorption mechanism. First one is resonance absorption and inverse beam-Stalling absorption. Resonance absorption occur at scale length greater than 1. In case of P-polarized light, light is efficiently energy transfer occur when the wave electric field component align with the plasma density gradient near the critical surface. And in the case of S-polarized light, the key mechanism is inverse beam-Stalling, in which electron ion collision in the presence of laser field lead to the enhanced plasma heating. These are the theory and governing equation. What is the linearly polarized light wave? There are two kind of linear polarized wave. First one is S-polarized wave, when the electric field component perpendicular to the plane we call the S-polarized, and the electric field component parallel to the plane of incidence we call P-polarized light. And in case of circular polarized light, it is the superposition of S and P polarization with the phase difference of 90 degree. And these are the governing electric field wave equation in case of electric field and the magnetic field, because in case of some polarization, the solving of electric field equation is easier, and in case of some polarization, we solve the magnetic field wave equation. Okay. This is my dielectric function in case of cold, collisional, and unmagnetized plasma with the immobile ions. Here, when the light is incident obliquely on a inhomogeneous plasma, basically linearly inhomogeneous plasma, it will reflect to the reflection point where density become critical density into cos square theta. And after that, some part of this transmit to the resonance point and excite the Langmuir wave excitation. Okay. Reflection occur at when epsilon is equal to sin square theta, and the resonance point is where omega become omega px. This is the typical analytical, numerical, and PSSI++ simulation parameter. The intensity is approximately 10 to the power 18 watt per meter square, and the wavelength 835 nanometer. And I choose the and solid variant critical is approximately 1.3795. Okay, this is the electron density profile. For x less than equal to the 0, we have a solid target, and from 0 to the L, we have the linearly varying density profile. Basically, we do for the quadratic cubic. My code is valid for q is equal to 1 to 5, but now I am presenting from q is equal to 1 for linearly varying density profile. And the collision frequency is also depend upon the electron density. Basically, it is proportional to the electron density. Okay. Firstly, I discuss about the field profile of the S polarization normal incidence. In case of a normal incidence, the governing equation of oblique incidence is written here, and their analytical solution is a function of it is a spatial function proportional to the Airy function, and we validate our result with the numerical, analytical, and simulation result, which is perfectly matching. Okay. We see that at approximately 1.6 is the reflection point where electric field become maximum. Field profile for the S polarization, this is the analytical solution for the P polarization light, and we also validate for numerical, analytical, and simulation result. At x is equal to 5, the laser incident, and approximately 2.6 or 7, the laser will reflected. Here we see that when we increase the angle of incidence, this is basically a normal incidence. Okay. When we increase the angle of incidence, this is approximately 30 degree. We see that the reflection point shifted towards the vacuum plasma interface. Okay, this is the field profile for the oblique incidence. These are the governing equation which I derived from the oscillating wave equation for a magnetic field for BZ component, EX component, and the EY component. And this is the field profile for oblique incidence is approximately 14 degree. This is the EX component of the electric field. The left one is the for 13 degree, and the right one is for the 30 degree approximately, with the collision frequency 0.001. Why I take the collision frequency 0.001? Because in the numerical means basically RK4, and another one is the PIC simulation to validate our result with the scale length of 5 lambda. Here we also see that at angle of incidence increases, reflection point shifted towards the vacuum plasma interface, and the resonance point peaks at approximately 1.3 or 4. These are the EY and BZ component of the field profile at 13 degree and 29 degree. Okay, this now I will discuss the field profile for the circular polarization at normal incidence. For circularly polarized light, light is incident normally on an inhomogeneous plasma. Electric field is a 90 degree phase for composition, it is superposition of S and P. So this is the governing wave equation, and I derived it the analytical, which is the proportional to the spatial function called Airy function. This is the field profile for the circular polarized light normal incidence, where EX, EY, BY, and BZ, which is perfectly matched with the numerical, analytical, and the simulation results. Okay. This is the field profile for the circular polarization at the oblique incidence. At 14 degree with scale length 5, which perfectly matches the numerical and the simulation results. Okay. Now absorption at the different polarization. Absorption, okay. For calculating the absorption, right now I do only for the, I only solve the wave equations. For S polarization at x is equal to L, the numerical solution must matches that the incoming and the outgoing plane. From using the boundary condition, one can derive the reflectivity of S and P polarized light wave. Okay, in case of as polarized light, inverse Bremsstrahlung absorption is a dominant phenomena. In this case, when oscillating electron of the electromagnetic field undergoes collision with the ions leading to the energy loss and the wave and the heating of the plasma. This is the typical WKB approximation for the fractional absorption. The left one graph is the absorption versus angle of incidence, and here we see that as we increase the scale length, the absorption increases because the light, when we increase the scale length, light penetrate more into the plasma. That's why the absorption increases. And secondly, we see that we increase the angle of incidence, absorption decreases because critical layer shifted towards the vacuum plasma interface. So the laser penetration in the plasma is less. That's why the absorption decreases while increasing the angle of increases. And the right one graph is the validation of our numerical and analytical solution at the scale length of 5. Okay, this is the typically contour plot of the S polarization. Here we see the same type of a result. When the angle of incidence increases, absorption decreases, and when the scale length increases, absorption increases. And the second one is the collisional effect. When we increase the collision in case of as polarized light, the absorption mechanism increases. Here is the observation. Absorption peaks at theta is equal to 0 degree due to the maximum wave penetration. At higher theta, the critical layer shift towards the vacuum plasma interface, reducing absorption. For scale length greater than 1, a gradual density gradient allow deeper penetration, increasing absorption. Now, absorption for p-polarized light. In case of p-polarized light, okay, it will occur when the component of the electric field along the density gradient interact with the plasma, although the main wave is reflected at the turning point, but our evanescent part of the field can penetrate up to the critical density layer where the wave frequency matches to the local frequency. This leads to the energy transfer from the wave to the electron, resulting the absorption by the plasma. This is the famous fractional absorption formula, which is a Denisow function. Okay. Here is the absorption versus angle of incidence, where we see that when we increase the angle of incidence, first the absorption increases at a particular angle, which is particular angle called theta optimum angle, and then decreases. And the second graph is the basically Denisow function, which is theoretical and numerical matches at absorption is maximum at approximately 0.8. And this is the variation of angle of incidence at different collision frequency, absorption or scale length. Okay. Summary for electromagnetic field profile. In case of S polarized light, analytical, numerical, and the simulation results agrees well, shows that the field follow the Airy function profile. The reflection point occurs at epsilon is equal to sine square theta and shift towards the vacuum plasma interface as the angle of incidence increases. In case of p-polarized light, for p-polarized light, BZ profile exhibit the rapid decline in the magnetic field after the reflection point epsilon is equal to sine square theta. While before this point, the magnetic field amplitude oscillate as the standing wave due to the interface of incident and the reflected wave. A sharp peak of EX profile is observed at the resonance point caused by the alignment of electric field with the density gradient. In case of circular polarized, we saw the same phenomena because it is the superposition of S and P polarized light. In case of absorption mechanism, in case of S polarized light, absorption dominated by the inverse Bremsstrahlung, peaks at theta is equal to 0 degree. And when theta increases, reflection point shifts toward the vacuum plasma interface, reducing interaction and the absorption. For the scale length greater than 1, gradual density gradient enhance absorption due to the deeper penetration. In case of p-polarized light, absorption governed by the resonance absorption. For theta at the theta optimum, which occur when tau is equal to 0.8, the EX, the evanescent field is strengthened with increasing theta, peaking at theta m. For theta greater than theta optimum, the distance between the critical layer and the turning point increases. Due to this lower coupling, reducing the absorption. The parameter tau, basically the tau parameter is profile invariant. Whether I choose the linear, quadratic, or cubic profile, the tau will always. So okay, the maximum absorption will always occur at 0.8. Okay. Thank you.
Thank you, Shakti. So finishing well within time. So presentation is open for discussion. Any question, please? So maybe I can ask. So you are looking for the electromagnetic profile, how it is interacting with plasma for different polarization and what kind of absorption?
What type of absorption phenomena takes place? For the large scale length, because in case of a small scale length, the vacuum heating or the Brunel absorption phenomena take place. But the field profile does not change, but the absorption mechanism was different. So I will studying on
So it
that.
is for large scale length, you are
This is for
sufficiently large scale length where
sufficiently large
resonance,
scale length.
resonance absorption.
Because that the analytical solution all are approximate, WKB is approximation. So that's why I choose large scale length.
And how you take into account this evanescent field also for that resonance, right?
Yes.
Uh-huh.
One can also, when the light goes into the plasma and reflected from the critical surface, the evanescent part go to the one
To
can
the
also-
critical end. So what is the uniqueness? I mean, what is anything difference you are seeing than what is obvious or something parametric regime you have tried to explore something?
Basically, I will try to see the absorption in case of circularly polarized light. That what type of we know that in case of depolarized light what type of mode conversion we have. But in case of circularly polarized light, we want to know that what type of mode conversion takes place in that, and what when the circularly polarized light, either it is left or right circularly polarized incident on the plasma. Incident of plasma, how absorption varies with the different
So that
scale
would be
length.
a kind of
I will try to derive with analytics.
same formulation you will be.
Yes.
Yeah. Okay, so let's thank Shakti for this nice presentation. Yeah. So the next oral presentation from Shikha Misra from RRCAT, and she will be talking about effect of gas density profile on high energy electron beam characteristics in laser plasma, etc. Shikha, please. Yeah.
Okay. Good evening, everyone. This is Shikha from RRCAT. I work in laser plasma division with Dr. Anand Murthy and Vipul Arora sir. So right now I'm working on electron acceleration from laser plasma accelerator. The title of my talk is Effect of Gas Density Profile on High Energy Electron Beam Characteristics in Laser Plasma Accelerator. This will be the outline of my talk. First, I will discuss about laser plasma electron acceleration, then the basics of laser wake field acceleration mechanism. Then I will come on effect of gas or plasma density on electron beam parameters. How can we control electron beam divergence by making use of plasma collimator, which is the main theme of my talk. Experimental details or setup that we have used for the present experiment. Observations which say that reduction in electron beam divergence has been observed from 10 milliradian to 2 milliradian. That means plasma lensing is happening. Along with that, we have also observed electron beam energy enhancement from 150 MeV to 500 MeV. And finally, I will conclude my talk. Okay, so what is laser plasma electron accelerator? Dr. Arora has already done my work for the first slide. Electron cannot gain energy directly from the laser because that field is oscillating in nature. So now, how electron is gaining energy from the laser plasma electron accelerator? The second word is plasma. So here, plasma is acting as a medium between laser and electrons which are accelerated, those electrons are plasma electron only. So whenever laser pulse passes through a plasma, it perturbs the plasma state by separating electron and ions. So due to electron and ion separation, huge electric fields are created. For example, for a plasma density of 10⁻18 per centimeter cube, electric field will be 100 gigavolt per meter, which is huge. And also, that field will be electrostatic in nature. That means, in this case, electron can gain energy from the plasma. Now, for laser strength parameter A0 more than 2, which is nothing but signifies the intensity of the laser. Non-linear interaction between laser and plasma will occur. If we want to accelerate electron to GeV energies, we have to work in the 3D non-linear regime only. So this is a simulation picture we use typically to explain laser wake-field acceleration mechanism. Here, when laser pulse passes through this plasma, it expels electrons radially from its path due to the ponderomotive force. Now, expelled electrons stream back due to the ions which are left behind the laser pulse. Now, the streaming of the electrons create an ion cavity type structure, which we also call bubble. So this bubble is nothing but a spherical structure surrounded by a dense sheath of the electrons. So this charge separation of ions and electrons create huge fields that I explained earlier. To create a near spherical shape bubble, A0 should be between 2 to 4, and this condition should be matched, where Kp is the plasma wave number, omega naught is the laser focal spot, and R is the bubble radius, and tau is the laser pulse duration. Now, if I take one bubble, there can be two types of forces working on the electron. First is longitudinal force, which gives acceleration to the electron and control energy E and Pz, longitudinal momentum, which is nothing but the E by C for a relativistic electron. And second force is transverse force, which will try to focus the electron beam and hence control the radial momentum of the electron. And so it will control the divergence, which is the ratio of the radial to longitudinal momentum. So now, if electrons are injected in the bubble, it is accelerated along with the focusing forces. So it will come out as a beam from the laser plasma accelerator. Now, since plasma is acting as an accelerating medium here, the plasma density has an important role. The electric field which is created is directly proportional to the square root of the plasma density and the dephasing limited acceleration length. This length is the distance up to which electron will see the accelerating phase inside bubble. So that is proportional to the inverse of the cube root of the plasma density. And next is focusing that I talked about is the field which is responsible for the focusing is proportional to the square of the plasma density. And last, the plasma length should be greater than the at least L maximum, which is the dephasing length, to accelerate the electron up to the maximum available energy. Now, since the main theme was to control the electron beam divergence, first I will discuss why I need low divergence beam. First is, low divergence is essential for efficient staging, where we accelerate the electron beam in two stages. First stage is the injector stage, and second stage will be booster stage. For low divergence electron beam, the coupling between two stages will be easy or efficient. Next is, if we want to inject electron beam in the FEL, for that also we need low divergence electron beam, at least less than 1 milliradian. Low divergence electron beam also enables high resolution imaging in radiography applications. It promotes directional and coherent X-ray generation, and more so, it improves the transport efficiency and reduces beam losses in beamline systems. So how I'm controlling the electron beam, how can we control the electron beam divergence? For a usual beam, if we try to focus the beam by applying electric or magnetic field, it will be focused, but at the same time, it will have a radial momentum component. So if I just remove the field, the beam will try to blow up with some divergence. The same case will happen in the plasma. I talked that inside plasma, or in this case bubble, electron beam will be focused due to the transverse forces. And now if I suddenly cut the plasma, like if there's a sharp boundary between plasma and vacuum, then electron will suddenly blow up due to the radial momentum component. And as it propagates, its beam size will keep on increasing. Now, on the other hand, if I make the plasma and vacuum boundary if I make a slow density fall at the plasma and vacuum boundary, then first, since force is proportional to the plasma density, that force will become weaker. And weaker force will generate to a low divergence beam. So electron beam divergence will slowly become low at the exit of the plasma and vacuum boundary. And as it propagates, its beam size will not change much. That means if I create a slow density fall at plasma and vacuum boundary, then we will get a collimated electron beam. Why it is, what is the benefit of plasma collimator? First thing, I'm focusing the electron beam along with the acceleration. So it will be a compact setup. Next, large fields are available to focus the electron beam. So it will, the task will be done in mm or centimeter distances only. And it will preserve the electron beam charge because all electrons are accelerated inside the bubble only. Okay, the setup we have used for the experiment. I have used 150 terawatt titanium sapphire laser system. The laser was focused using a 50 centimeter off-axis parabolic mirror on a gas jet. The gas I have used was nitrogen, and gas jet length was 1.2 mm. The plasma density I worked on in the range of 1 to 10 into 10 raised to the power 18 per centimeter cube. So laser was focused on a gas jet, and after laser and plasma interaction, electron beams were generated, which was first detected on the phosphor screen P1 to get the electron beam profile and pointing information, and then it was dispersed in the magnetic field of the order of 1 Tesla and large in size, and then its deflection distance was measured on the phosphor 2 to get the electron beam energy information. Now, since the main focus was to change the vacuum and plasma density slope, the plasma density slope. So how we did that? We implement a simple method to tailor the gas or plasma density profile. We change the laser plasma interaction height from the nozzle axis. In this figure, we have changed the Y1, Y2, and Y3. So this height, the variation in this height will result in the increment in effective plasma length. It reduces the peak plasma density. And additionally, what we wanted, it slows down the rise and fall of the gas density profile. Now, to see if it really happened, we recorded interferometric data by using a probe beam. So these are the results for 2 mm laser interaction height at 3 mm and 5 mm. When we go from 2 mm to 5 mm, fringe shift in longer region indicates that the plasma length has been increased. Along with that, lower fringe shift at 5 mm is the signal for reduced plasma density. We also measured the edges of this profile to confirm that if the fall of the plasma density has been implemented. Okay. Now, to check the collimation or lensing effect, we recorded electron beam profile at all these positions, 2 mm, 3 mm, and 5 mm from the nozzle axis. Here, x-axis and y-axis show the horizontal and vertical divergences of the electron beam. Color scale shows the electron beam charge. When we go from 2 to 5 mm, electron beam divergence reduced from 10 milliradian to 2 milliradian. That means collimation is happening in the inside plasma when we change the laser interaction height or we change the gas density profile at the plasma or vacuum exit. So, our main theme was to control the electron beam divergence only. But what is the effect of that gas density profile or effective plasma length on the electron beam energy? We also recorded electron beam spectrum at all heights. So, what we observed, we saw that at 2 mm, the electron beam energy was 150 MeV. It is the maximum energy, which changed to 450 MeV for 3 mm and 5 mm respectively. That means, along with the plasma collimation, electron beam energy is also increasing with the changed plasma density profile or length. That means here plasma collimation along with the energy increment, like experiment is beneficial both for plasma collimation as well as for energy enhancement. Now, Finally, I will conclude. We have implemented a simple method to tailor the gas density profile just by changing the laser interaction height from the gas jet nozzle. Next, we observed plasma collimation. The divergence changed from 10 to 15 milliradian to 2 to 4 milliradian at 3 to 5 mm heights due to the smoother density gradients. And along with that, the higher laser interaction height reduces the peak plasma density, and which results in longer acceleration length, because dephasing length is inversely proportional to the plasma density that I talked about earlier. That means lower plasma density is helping in the electron acceleration. Thank you.
Thank you, Shikha, for finishing your presentation within time. So talk is open for discussion. Any question, please?
So actually the talk was real nice. I would like to ask you about, you are working on like dispersion, right? Dispersion or like to reduce the dispersion of your wave, right?
Divergence of the electron.
Yeah, divergence. Yeah. So actually are you using jet to reduce the collimation to around 5 to 2 milliradians, right? So instead of we can use plasma, like you can use waveguide, right? Cylindrical waveguides, or so you can reduce this 2 milliradians to further down of less than 1 milliradian. So is there any future work like?
Yes, people are doing that. It's like, but in this work, what I have shown, beam collimation is happening along with the acceleration. Laser and plasma interaction is happening inside the gas jet. So it is used to accelerate electrons. Now, along with the acceleration, I have tailored the exit profile of the plasma inside vacuum. I have not used other gas jet. Within acceleration only, collimation is happening. So, if you want to further reduce the divergence, you can use waveguides or quadrupole or other optics. But here, what I want, electron beam divergence should decrease inside the acceleration step only. So that if I want to use another acceleration stage, I could couple the maximum electron beam charge to the another gas jet.
Or like to reduce the devices which you can use. Right now you are only having the direct acceleration happening, right?
No, direct acceleration is not happening here.
No, what she is telling is during the acceleration process itself, if you are able to control the beam parameters without any adding additional thing, it would be better. Of course, you can use magnetic optics further to control the beam parameters. Or what do you mean by waveguide? I mean plasma waveguide or something else?
Like waveguide, like cylindrical waveguides.
Any material you would not like to put your electron beam. Maybe plasma as a optics you can use. Like here also it's a kind of that only.
Yes.
So, but it is in the acceleration generation itself. Of course, you can use many. After that, the beam has come out. You can use other things to manipulate the beam. Yeah. So it's at the source itself. Yeah.
So is there any future like planning to add waveguides to this thing which you are doing?
Yes, plasma waveguide as a second stage we are planning to add to focus or transport the electron beam for further applications.
So is there any open projects which we can also partake kind of?
You are always welcome to come and discuss with us about future projects.
Thanks.
So it's not just formal welcome. Let me use it for outreach also here, as you are showing interest. So those students who want to do PhD, like already you are registered, we have HBNI, Homi Bhabha National Institute. Earlier it was not she is employed there, she is doing PhD, but we can take external students also through Homi Bhabha National Institute, which is a deemed to be university under Department of Atomic Energy. So there is a JEST examination for that. One can appear in that and then opt for the PhD at RRCAT, and those interested in laser plasma or like that. And those who have done PhD, they can also come to us as a postdoc through either through DST or other fellowships, or now in our project we will also have position for RA. So through that also one can, like any idea or any thing that somebody wants to implement, can join us. Not just formal invitation, but through a proper channel. Okay. So any other question, please? Yeah, there was one question. Yeah.
Thank you. I have a question that you said that when you tailor the plasma profile, your means along with the collimation, you also get energy increase.
Yes, sir.
But why that should happen means because the beam will interact with the plasma and then it should lose the energy rather than gaining energy. Means if I'm not correct.
No, sir, you are correct. Like, let me go to the one slide.
Maybe you can answer without slide also. Yeah.
There are two things. First is electric field, which is proportional to the plasma density. And second is the phasing length, up to which electron will see the only accelerating phase only. That is inversely proportional to the plasma density. That means if electron will see the sufficient field, which is E, but it should see that field up to the longer distances, which is inversely proportional to the plasma density. So when I'm going to the 2 mm to 5 mm, that peak plasma density is reducing. That means my accelerating phase, the distance up to which it will see the accelerating phase will increase with sufficient electric field. So electron will gain higher energy.
Maybe what he is asking is if you may have to, why a beam should not lose energy rather than gain energy if longer propagation in the plasma, right? That's what his concern is. So till the wake field is there, till the laser is strong enough to generate the accelerating field, it will gain energy. But once it is out of that field and then you have a plasma medium, then it will start losing energy by its own wake field generation. So it is not happening that here. It is still in the laser accelerating field created by the laser in the plasma for longer length. As she said,
Yes,
the density
yes,
is
yes,
small.
yes.
So the field is still strong enough to accelerate the particles. The beam has not extracted from that bubble and gone into the
Yes,
plasma medium.
and we started with a smaller gas jet length.
Gadgets, yeah.
So that if we go up to the higher length, that depletion will not occur inside the laser. Laser will be capable in generating plasma waves and hence in acceleration of the electrons.
So you are right. If the beam itself will go into plasma, it will start losing by generating its own wake field.
Yes.
But till the wake field, this field is their laser created field. It will keep, and it is in phase, not dephased. So it will keep accelerating. Yeah. Please give mic. Yeah, please. Mic दीजिए ना वहाँ है उनके पास. हाँ. Please use mic. Yeah.
When you said that you have that vacuum break, means and then if you have vacuum, then it will diverge.
Yes.
But if you have a plasma, then it will not diverge that much. It will be a collimated beam.
Yes, sir.
So it is after the laser. I thought that that's what I'm asking, that whether if you have that plasma again, and the beam is passing through that, then it should not gain.
Maybe you go to the next slide, जहाँ पे आपने collimation दिखाया है. Yes, like that. So.
Okay. Sir, I haven't shown here. I should have shown here a transition of another bubble. I'm cutting the plasma sharply in both cases, but here, since the density is falling slowly, so there will be another bubble here, behind the laser pulse only. Laser is guiding the bubble or plasma.
So there is a gradual decrease of plasma. This figure is misleading, you are right, because it is showing a sharp cut.
Yes,
so it is a gradual decrease and bubble is still moving through that gradual decrease in the plasma.
Yes.
So it is not the end of the acceleration process.
Yes.
So that's
Or
what
a laser pulse should be here.
Yeah.
Yes.
Any other question, please? Okay, I think let's thank Shikha for this nice talk. So we have last talk of this year, one more oral presentation by Amya, right? quasi-static transverse sheath electric fields for boosting direct laser-driven electron acceleration.
Yeah. So hello everyone. I would like to thank PSSI for giving me the opportunity to talk. So my name is Amay Parab and I am from TFR and like today I will talk about the laser matter interaction in solids. So like already Professor Arora has given a brief introduction about the solid interaction and ion acceleration, and like Shikha had also told about the wake field acceleration, electron acceleration. So like I'll try to talk about the mix of it, like talking about the electron acceleration in the solids. So next. Okay, so why the electron acceleration is important and like what are the applications out of it? So like so electron accelerations can be used for making the compact X-ray sources and the gamma sources, which can be used for the ultra-fast X-ray imaging. Next there can also be some medical applications, like we can generate secondary protons for like medical purposes as well. Next, these electron sources can also be used to make like the compact particle accelerators, which can be injected for the FELs and the next generation field electron acceleration. And then lastly, we can also help to understand what is happening at the astrophysical scales, and like we can try to mimic all the conditions in the lab. So like next, I will just talk about the background on like relativistic laser matter interaction and how it works. So we have a target. So like that target can be any of the foil, which is a few microns or like few nanometers as well. So like so the material that can be chosen can be varied from aluminum, gold, and anything, any metals. Next, we have a laser which comes at 45 degrees. So the laser parameters are in the range of 800 nanometer, few joules of energy, and the pulse width of around 30 femtosecond, and like a few micron for focal spot, and the polarization is p polarized normally, and it creates a plasma, and from that plasma we have the fast electron jets, which are the first to react and they just fly off from the front as well as from the back of the target. Due to the charged electrons, so the electrons getting thrown out of from the rear of the target. So like we create the sheath field at the back and at the front of the target. So these electrons can be of the range of keV to the MeV range for the few joules of input of 800 nanometers. So like this is the positively charged sheath field, which we are talking about. And next we have the TNSA protons and we have the low energy electrons, which are followed up from this interaction. So next I want to talk about this positively charged sheath field. So also from this interaction, we are so we get megagauss magnetic fields, we get the X-rays, and we have all sorts of particles coming out of the interaction. So next I will talk about, once we know like what is the interaction that we're talking about, I want to ask some few questions for which I will answer. So first question is, can the transverse static electric field enhance particle acceleration? Next we know that one common phenomena which people in solid matter interaction struggle is like making the surface electrons accelerate. So for the surface electrons, we need a special fabrication of targets such as gratings, or else we need to trigger the surface plasmon resonance or like some kind of surface waves to excite the electrons onto the surface. But like my question is, can it be done on the flat target very efficiently? Is it possible? And the next thing, the femtosecond pulse, which I talked about, it's a 30 femtosecond pulse, but on a log scale, if we see the actual femtosecond pulse has a huge pedestal. So the main interaction starts, so the main interaction starts very early on, around picosecond scale. The contrast, so the pedestal is enough to trigger the ionization, which can alter the conditions before the main pulse arises, which can change the energies of the electrons that we talked about. So like ionization can begin at a picosecond before the main interaction. So like, can there be an electron acceleration scheme which is less sensitive on the pre-plasma scale length? So like, I'll try to answer these questions. So next, the role of the sheath as we understand. So like, this is the interaction we know about. And like this, so like already Dr. Arora sir has talked about this positive potential, which helps to accelerate the ions to the MeV scales in a typical laser matter interaction. So next, this sheath field plays a negative role in like retarding those electrons, since it helps in accelerating the ions. So like the sheath field has been the culprit to deaccelerate the electrons and not having the enough energies into electrons. So like there are a lot of papers about the TNSA electrons, which TNSA ions, and they also deaccelerate the electrons. So the conclusion is the sheath field plays a negative role. So my question is, can we do reverse? Can we use the sheath field to accelerate the electrons as well? Is there a mechanism? So next, can we modify the geometry to favor the electron acceleration? So next is, what if we have this interaction and we time a second pulse into the rear of the target? In the presence of that sheath field, will there be surface electrons at the back? That's the idea. So like to check this phenomena, we use a 2D PIC simulation called as Smiley. It's an open source software. Next, I will talk about the simulation parameter. This is a typical simulation box. It goes around vertical, in y-axis is around 100, and in x is around 75 microns. We have two lasers. So the angle being chosen for the top laser is around 45 degrees just to increase the absorption and to create a stronger sheath. And the 70-degree angle for the bottom laser is just to have initially enough electrons onto the surface. And the target I've chosen is 2 lambda. The lambda over here is 800 nanometer. So the target thickness comes out to be around 1.6 microns, which is not very thin actually. So both of the lasers have the A0 of around A03, which corresponds to around 10⁻⁹ watt per centimeter square. If it is focused on a 3 lambda focal spot and a pulse width of around 30 femtoseconds. The total simulation time is taken to be around 500 femtosecond. And we have chosen an initial pre-plasma, which is of the 200 nanometer, which is a long enough pre-plasma in terms of the laser matter interaction. So next, the boundary condition is to absorb all the fields on all the boundaries and to remove all the particle once it reaches the boundary. Next, the diagnostics that we have chosen is we need to characterize what is the sheath, how is the sheath. We need to characterize the angular distribution of the electrons, where are they going and what are the energies of those electrons. And then we need to also track the particles so that we can understand how the particle is behaving in this scenario or the interaction. So next I will talk about the characterization of the sheath field, like how much is the sheath field and what are the, how strong is the sheath field. So like I've taken this a snapshot of one of the simulation during the simulation run. So the electric field is around, the laser electric field is around 12 to 15 teravolt per meter. And then if I do the Fourier filtering of this, we can see the harmonic orders in the reflected as well as in the incident. You can see the first order. So like what if I just remove all the oscillations? So like I would be able to clearly see the static field. So if I inverse Fourier this again, then I'll be left with the static field. And that static field is of the order of 4 into 10⁻�3, which comes out to be around 0.3 to 0.2 to 0.3 times the input laser field. So we can establish that the sheath field is around of the order of 0.3 if we are hitting on a 2 lambda target with an intensity, with an A0 intensity of 3. So now that we know what is the sheath field, now let's talk about the electron distribution and the spectrum which comes out. So like before that, I will talk about like building the references. We don't know what energy range are we talking about. So like let's have the system where we have just one laser at the top. So the A0 I've taken is √2 times the I, because I want to dump double the energy, because eventually I will split it up into 2 lasers. So I want the A0 scaling. So I want √2 times A0, which is 3√2, hitting onto the same target with all the same specifications. And then I also have a scenario where I have only the bottom laser, so that I would like to know what are the angular distributions and the spectrums of those. So going to the spectrums, I have just 2 of the spectrums side by side. So the first, okay. So like, so the top part is the angular distribution. So the top hemisphere is the above part of the target and the bottom hemisphere is the bottom part of the target. So the radially we can show the energy of the electrons, and the angles show the angular distribution of electrons. The red curve is the integrated flux, which you can see, like where is the peaking of the electrons coming from. And then I have this one laser, and then the ESM which I'm taking, I just want to calculate the ESM of the surface electrons at the bottom part of the laser. So like what I'm doing is I'm taking the blue part, the blue shaded area, and then calculating the electron spectrum of it. And the electron spectrum comes out to be 9 to 10 MeV. And in the second case, where I have just the bottom laser, the electron spectrum is also around the same range. For the temperatures, I have fitted the Maxwellian, assuming the Maxwellian distribution, which comes out to be 1.4 MeV and around 1.28 MeV. So next, I will go to the case of two laser systems. So assuming in the experimental case, we will split the same laser by beam splitters to have two lasers from the opposite end. So next in the presence of two lasers, this is the geometry, and I also added the scale length of 200 nanometer. One comes at, let's say the top laser comes at around t timestamp. So the second laser comes at a different timing of t plus delta t. I will define the role of the delta t in the future slide, but for the best possible scenario, I would like to show the angular distribution and the electron spectra. So the spectra in the earlier case, even with the double energy dump, it was around 10 MeV, but right now in the two energy case and the best timing situation, it comes out to be around 15 MeV, which is an increment of around 5 MeV. And the electron distribution also you can see that it is slightly higher in the bottom part because the particles are being guided around the bottom surface. So like why? So now we need to look closely. So to just summarize, I have all of the three side by side. The first two are the single laser setup, and the last one is with the setup which has the both of the lasers. So let's look closely to this. I have a video where I have the particle tracking. I will show this. Okay, so both of the lasers are coming. If I go slightly here, I will pause over here, and then for the second. Okay, so if you see the without sheath laser, if you see the particle just follows the laser electric field and it's slightly away from the sheath field. But in the second case, the particle is defaced from the laser and the particle stays along the surface. So the single electron trajectory slightly behaves differently. So the origin is approximately same, and the starting position of the particle and the energies are approximately same. So again, if I go to the next slide, so like I have chosen randomly 1,000 particles, and then tracking the particles and their trajectory, I can see that the x-axis and the y-axis, the gray part is the target, and then as a part, so the color bar indicates the energy gained by the electrons, and then you can see that the electrons in the focal spot gain the maximum number of energy. Next, if I take the instantaneous position of the same particles, you can see the scales x-axis is around 32 to 44, which is almost slightly away from the focal spot. The middle part is within the focal spot, and then the last part is away from the focal spot after the laser has gone. So the particles have gained the energy in between that focal spot. Just to then I want to understand what happens, like what is the role of the sheath field around it. So if you remember, we did the Fourier analysis of the sheath field and we removed the oscillating part. If we do the same for this, then we have this scenario where I have, this is the same overlaid particles, but the field now here is I have removed the oscillating part. So now you can see that the particles are slightly behind the sheath field. When they are accelerated, they are in the sheath field, and after that they gain the energy and they continue traveling along the surface of the direction. So next, to show the phase space, I will try to, yeah, okay. Okay, so like this is the same phase space which I'm talking about. So I can see that there is a spike of energy gain, and I can say that this is the kind of the acceleration length I'm talking about. So then to understand the dephasing and the injection, we use a 3D single particles simulation, which was done in CEBS by Dr. Bhushan Paradkar. Next, we have two cases where we have a single particle into the laser, same parameters, with the top one is without sheath, and the bottom one is without sheath. Here we added the external sheath on purpose of the same magnitude as we talked about, like 0.2 times the A0, same boundary condition, and we are just tracking the single particle trajectory to understand it better. So the next part, I will show you the result. If there is no sheath field, the particle in vacuum will just gain energy, lose energy, and eventually the net gain is very small. But the same thing in the presence of the sheath field, it does have a similar profile as we saw in the phase space. The gains here are more because the particle stays in the phase of the laser longer. But like this exercise is just to show that the role of the sheath field, like it tries to inject itself into the laser very efficiently in the presence of the sheath field. It does not gain the energy from the sheath field, but it helps. It acts like a catalyst into the interaction. So next, where the particle is originated and where the particle is injected, does that play a role into that interaction? So we have, let's say, 1,000 particles, 10,000 particles injected at different position with respect to that sheath field. And we have this plot. So if the particle originate slightly before the sheath field, it helps to gain them slightly higher value, higher gain. So like this is the gain at the end of the simulation. And next, if you see that it matches with the PSC where the particles were slightly behind the sheath field, and further they enhanced in the presence of sheath field. Next, I will come to the last section, which is the timing. How crucial is the timing of the two lasers, and like, is this feasible for this petawatt class laser and the future lasers? So next, we know about this delta T timing between the two lasers. So the top part is the evolution of the sheath field versus the delta T. When the particle was being accelerated, what was the value of that sheath field is what I've showed. The negative scale shows that the particle is hitting the particle is accelerated, and then the sheath field comes, which is actually very small value. And then in the positive cycle, you can see a jump in the sheath field. And the bottom part is the electron temperature, where both of the lasers are A0 3 and 3. So the red curve shows that. And if both of the lasers are A0 10 10, so the blue curve shows that. And you can see that there is a gap of around 7 cycles to 8 cycles between the two of the lasers, where you can see that the electron temperatures of those for those on the surface stays to be constant. So like we have a window of around 7 to 8 cycles in which we can do this accessible, which for 800 nanometer, it's around 15 femtoseconds. So like we can tune the lasers by our delay stage in the future experiment, for which we are trying to plan. But then this is the rough idea of how it scales. So I'll come to the conclusion. We are able to efficiently accelerate electron two laser systems. So like no special fabrication is required because we can do it on flat targets. Shows that the sheath electric field does help electron acceleration if we change the geometry. And then the not so good contrast can also serve the purpose of it. And then it is scalable at high petawatt class lasers. And then I would like to thank the TFR family and then Bhushan for doing the single particle code. These are the references, and thank you.
Okay, thanks. Presentation is open for discussion. Any question, please? Right, so maybe just for my clarity and maybe to the audience, it's not clear to me. Yeah. You have? Yeah, please take. Audience first. Yeah. Just please use mic. Yeah.
Spatial variation of electric field in the sheath.
Okay, so the spatial variation, we have chosen it to be Gaussian because in the simulation it showed to have a transverse Gaussian profile. And it evolves to be a Gaussian profile, but it decays as a function of time.
So where is the peak of that Gaussian mentioned there?
So the peak of the Gaussian is, so like here if you see, this is the peak of the Gaussian is somewhere over here, and it decays as a function of time, space as well as a function of time. As a function of time, I have shown it here. As a function of time, it decays, and as a function of space, transversely it decays.
Does it depend on the delta T then?
Yes, it does depend. So the individual sheath field of single laser has nothing to do with the second laser. So the individual sheath field has no role on the how does second laser when it is hit. So no, actually.
Second laser doesn't produce any sheath, ion sheath.
So So it does, but it takes time to generate. So if you see the bottom plot, the acceleration delays by 2 lambda. So the 2 lambda is being governed by the thickness of the target. So if I increase the thickness, the acceleration will delay because the fast electrons will take 2 to 3 lambdas more to travel, exit the surface, and then create the sheath. So the bottom laser will take time of its own to create its own sheath.
It is the lambda also which plays a role.
Yes, yes, it does. It does. Lambda plays a role in creating the sheath field. Yes.
Okay, any other question? Yeah, just for my clarification, maybe. So it is the fast electrons generated by the first laser, which is going to the rear surface, and then the sheath field generated by the second laser on the rear surface is accelerating those electrons, or what is happening?
No. So I am not tracking not a single electron produced by the first laser. All the electrons are produced by the second laser. The purpose of the first laser is only to create the sheath.
So that sheath field is by electrons only, na?
Yes. Yes. Exactly.
So what happens to those electrons?
Those electrons, I chose not to track them, but the angular distribution covers.
So this enhancement is only at the rear surface?
At the rear surface. If we alter the timing, and so maybe we can have the electron enhancement at the top as well. Because if you alter the timing.
Yeah, I understand. Okay, maybe much more to think about. Okay, nice.
Okay.
Any other question? Yeah, let's thank.
Yeah, thank you.
Thank you. So with this, we come to the end of this session, and session is closed. Yeah, thank you.
Session Chair Professor Anand Murthy to kindly come on the stage and present a memento to our session speaker, Professor Vipul Arora. Sir, please come on the stage. I also invite Dr. Nishan Sese to present a memento to Professor Anand Murthy, chair of this session. Now I invite all oral talk presenter from this session to kindly join us on the stage. Professor Vipul Arora, sir. So now this is the end of the first day. Thank you all for your active participation and insightful contribution throughout the day one. Wishing you all have a pleasant evening and night. Looking forward to another exciting day tomorrow. Thank you so much, everyone.